hiyo hii ejected ita take place. So this is what is happening in the ejection of the electron. So as you see that this is the ejection of electron from the metallic object when hit by high energy photon. So this is the metallic object, as you see. Remember here we are talking about the ejection of electron. How do this after this a metallic object passing through that heat or distant tube and the ejection occur. So you can see that low energy photon ambayo tunaangalia ile energy, electron not ejected, kwa sababu tunaona kwamba electron lazima awe na specific amount of energy. Maana yake kwamba minimum on that ndo tunasema kwamba kuna hiyo the challenge, au tunasema kwamba electron not ejected. But also this in this side high energy photons ambayo hapa ni kwenye maximum not minimum, you can see that electron are ejected, and the different the color here are observed. Different color here are observed: red, orange, yellow, green, blue, indigo, violet, whatever. So you can see that this is due to the increasing of the energy. So as the energy increase, ndio maana tulisema kwamba this color will be displayed depending on the temperature. So the way energy increases is where this ejection or electron tend to be ejected. So this is the higher energy photon, and you see this is low energy photon whereby electrons not ejected. But here, as you see, the electrons are ejected, and this is our metallic object. So if the photon energy is too low, the electron is unable to escape the surface of the material. Kwamba kama energy au ile photon ni low, electrons zinashindwa kumove au kuescape kutoka pale kwenye ile metallic. That's why tumeona kwamba sehemu ambayo kuna high energy zile electrons zinakuwa ejected. Endapo hamna high energy or low photons, no ejection of electron. So an increase in the intensity of light beam lead to an increase of the number of photons in the light beam. Ni kitu ambacho kinaenda directly proportional. This led to an increase in the number of electrons emitted without an increase in the energy that each photon possesses. Each photon possesses. So thus you can say that the energy in emitted electron does not depend on the intensity of the incoming light. Kwamba ile intensity of incoming light no relationship, but on the energy of individual photons. Lakini kwa individual, only individual photon. So the effect suggests the particle nature of light, and such particle of light are called photons. Kwamba ile effect sasa ndo finally ilikuwa suggested or ilikuwa suggested as the photons. So by considering the Planck's equation, the energy of an individual photons is given by this equation ambayo we can term it equation 1.5, this one. Equation 1.5, whereby we have change in energy is equal to HV. Change in energy is equal to HV. Ile tuliona from the what? From the first equation of the Max Planck's, ambaye alisema energy ni directly proportional to that, the frequency. So now where H is the Planck's constant, V is the frequency of light, and this change in E is the energy of photon, ambapo kwa hiyo E of the photon ni sawa na change in energy. Ina maana change in energy tutachukua energy at the higher level minus the lower level, whatever. So here we have example. So if the wavelength of a certain electromagnetic radiation is this one, 1.20 centimeter, what is the energy of one photon of this radiation? Sasa tunaangalia au tunatakiwa tujue kwamba what are the energy of one photon. Kumbuka tushajua kwamba energy of one photon ni sawa na nini. So simple solution here. The first one, make the conversion of wavelengths into meter. I hope tulishaangalia hizi concepts za wavelengths, zile sehemu zake, how do they relate to each other. So here our wavelengths au ile lambda tulipewa in term of centimeter. So convert it to meter. Kuconvert kwa meter obviously uta times 10⁻². Only, very simple. Kwa hiyo hapa utachukua lambda, ambayo hii lambda, hii Greek symbol inamaanisha ni wavelength, is equal to 1.2 cm times 10⁻², ambayo inakuwa sasa na 1.2 times 10⁻² meter. This is our wavelength. So applying the Planck's equation, sasa tunakuja kuapply ile equation yetu ya mwanzoni kabisa, which is E is equal to hv. But we know that frequency is equal to what? So, as we know that frequency is equal to 1 over wavelength. 1 over wavelength. Therefore, is equal to C over wavelength. C over wavelength. Na C tunajua ni nini? C is the speed of light, ambayo every radiation or every light particle ina travel katika hiyo speed. Kwa hiyo C ni speed of light which is constant, lakini H pia ni constant value. Tunatakiwa tutafute energy of one photon. Sasa the wavelength ambayo ni lambda tumepewa, Hc tunayo. It is easy now to get our energy. So tuna substitute hapa tu kwenye hii equation yetu. E itakuwa ni Hc over lambda. H tunayo, C tunayo. Hii wavelength au lambda tulishapewa. So therefore utasubstitute value zako, ambapo as you see here cha kuzingatia ni SI unit. So here you have the speed of light, ambayo hii ni kama velocity, ambayo SI unit is meter per second, lakini pia una hii Planck's constant ambayo SI unit yake ni J second, joule second. But also you have the wavelength ambayo ni lambda, SI unit yake ni meter. So here it is mean that meter and meter will cancel, this second and second will cancel, and finally utabakiwa na joule ambayo ndio SI unit ya energy. So utazidishia hapa, utapata jibu lako, and finally the energy will be this one. Kwa hiyo energy of the one photon of the given wavelength is this one, is 1.66 times 10⁻25 joule. Utajaribu kuingizia kwenye calculator yako ili uweze kuprove. And then my student, after saying that, I would like to say this marks the end of our discussion. Thank you so much for watching. Welcome in the next discussion.